Here's a paper that asks a genuinely underexplored question. If you want to teach an AI model new facts without breaking anything it already knows, what if you never touch its weight at all? Right now, if you want an LLM to reliably know a big pile of facts, say your company's internal policy documents or new financial regulations, you have basically got two options and both have real problems. Full fine tuning works, but it's expensive and prone to catastrophic forgetting. The model starts forgetting old stuff while learning new facts. LoRa fine tuning is cheaper, but it doesn't fix the forgetting problem, and it struggles badly when you ask it about entity combinations it wasn't directly trained on. There's actually a document finding behind this. Teaching a model facts that go against what it already believes doesn't just fail quietly, it miserably increases how often the model hallucinates elsewhere. There's a third option that's existed for a few years: hypernetworks, where a second smaller network learns to generate weight updates for the first one. But the existing version of this called MENT or PropMENT work by transforming gradients, and that approach become unstable once you try to inject more than about 1,000 facts at once. Nobody had actually studied how any of this scales. This paper does something more direct. Instead of transforming gradient, they train a hypernetwork to look at a batch of facts and directly output a LoRa adapter, small weight patches. They get temporarily bolted onto specific layers of a frozen target model. The base model's own weight never move, not during training, not during inference, and crucially, this is the first paper to actually run controlled scaling experiments on this setup. What happens as you make the hypernetworks wider, deeper, give it a bigger target model to adapt, or feed it more facts at once? To even run these experiments, they needed a dataset big enough to support scaling law analysis. Existing knowledge editing benchmarks top out around 500,000 examples. Too small and too noisy, so they built their own called MegaWiki QA. 1.25 million multi-hop question answer pairs pulled from Wikidata 5 million's knowledge graph spanning 39 different knowledge domains. Clever part is the evaluation split. They held out three entire domains: philosophy, linguistic, and civil engineering. During training, they tested on the same questions rewarded by GPT 4.1 and on multiple choice versions of the same questions. Three genuinely different way to check whatever the model actually generalized versus just memorized phrasing. What they found: every single scaling axis they tested, hypernetwork with hypernetwork depth, target model size, and number of injected facts, produced smooth, predictable curves, no clip, no instability, unlike the gradient based methods that broke down past 2,000 facts. But here's the fun number that matters most for anyone actually building this. Scaling the target model matters far more than scaling the hypernetwork itself. Making the target model bigger improved result roughly twice as fast as making the hypernetwork wider or deeper. If you have only got a fixed compute budget, spend it on the model being adapted, not the thing doing the adapting. Head-to-head comparison is the real payoff. Against both LoRa fine-tuning and full fine-tuning, the hypernetworks loses slightly on fitting the training data itself. Fine tuning is bit better at that, but on every out of distribution test, unseen domains, evaded questions, multiple choice questions, the hyper network wins, and the gap gets wider as the model gets bigger. That's the opposite of what you'd usually expect from a more indirect method, and it's the paper's central finding. If you actually need a model that to generalize to real world fact, it wasn't spoon fed verbatim. This approaches scale in the right direction precisely as things get bigger. There's actually a catch. The author are upfront about a real deployability problem. In their largest experiment, the hypernetwork itself grew to about 2.5 billion parameters just to adapt a 1.5 billion parameter target model. You are nearly doubling your total footprint to get this benefit, which defeats a lot of the point. If you're trying to be efficient, they flag this explicitly as unsolved, pointing to future work on shrinking the hypernetwork itself, like sharing weights across layers or distilling it down after training. NaceAI released a MegaWiki QA and the training code publicly on Hugging Face. Worth a look if anyone works on knowledge injection or want to reproduce the scaling curves themselves. And thanks for watching.